Okay, yeah, good afternoon. So this is the final lecture, and this is the wrong slide. Okay, so this is the slide. Yeah, today is the final lecture, and we're going to finish week 13's topic, and particular today's topic is on quantum metrology and sensing. To talk about metrology and sensing, there's one fundamental principle that I should mention in quantum mechanics, that is the Heisenberg principle. So if you have two observable A and B, and if they don't commute, there is such relation of uncertainty. So I should define what I mean by delta A. So delta A squared is defined as, if you have a quantum state, you take A squared minus the average square, and similarly for B, so basically it's the standard deviation of the observable. Okay, you could also absorb so that you define this as A average square, okay, where A average is defined as the expectation value of A with respect to psi. Okay, so this is called Heisenberg's uncertainty because it relates to a standard deviation of two observable which are not commuting, right? So that means their uncertainty has a lower limit, non-zero limit in general, and this means that they cannot be each made to zero. Okay, so that's the uncertainty. For example, you have position and momentum. In quantum mechanics, these two observable do not commute. So the commutator of x and p is proportional to the reduced Planck constant. So that means using this formula, delta x times delta p is greater than the commutator evaluated with respect to this. And it doesn't matter what the state, this is always h bar. So this is the uncertainty relation between the position and momentum. And I'm sure many of you have learned this in your quantum physics. Okay, so Heisenberg initially regards such relation as the precision of measurement, or in this case, that's the error in the measurement and the disturbance it creates. For example, you're trying to make a measurement on the position of a particle, and then it creates some disturbance on the momentum of the particle. And in his interpretation, this delta P is the disturbance. Okay. However, looking at this formula, really the correct interpretation of the uncertainty is that these are intrinsic uncertainty, right? Because this is the uncertainty that you evaluate with respect to the quantum state psi of this observable. There's nothing said about measuring A that create a disturbance, although the both uncertainty need to satisfy this, right? So if they don't commute, then there is a lower limit on this non-zero limit. So the correct interpretation, for example, you can read Nielsen Tron or standard quantum mechanics textbook. It says if we prepare a large number of quantum systems in identical states, psi as here, right? So this is you trying to measure the square of the observable and the average of observable. That would define you a standard deviation. And this holds if you perform the measurement many times, and that's the average. Okay, then performing measurement on A on some of those. If you take some of these identically prepared state and measure A and some measure in B, then the statistical uncertainty of A and B satisfies such relation, such inequality. And in fact, there was an experiment performed in a group of physicists in Toronto that they perform a measurement using so-called weak measurement, so they can prepare, they can measure some observable, for example, A. After many average, they can measure its uncertainty. And because it's a weak measurement, they could also affect, measure how much the observable of B has been affected. And they came up with the conclusion that, in fact, these, if you interpret in terms of measurement uncertainty and the disturbance, then this could be violated. So this was an experiment described in this paper. So I'm not going into the detail, but just to mention that this has been tested. So the original interpretation of Heisenberg was not that correct. The correct one is stated here. So this is related to quantum mechanical non-commuting property of observable. But in classical physics, for example, position x and the momentum p, there's no non-commuting property like that. Then it assumed that you could measure them separately and arbitrarily precisely. So there's no fundamental limit in classical. So in classical physics. Okay, this is classical. So in quantum mechanics, when you perform measurement, you change the system. So you have some quantum back action. So that's interpretation and also intuition of Heisenberg. And if you repeat measuring the same system, you cannot obtain the original property because it has been changed. So although this Heisenberg's uncertainty, this in a sense is correct mathematical statement, but the interpretation has to be careful. Okay. And indeed, it's actually possible to resurrect Heisenberg's viewpoint, and you can really derive some uncertainty relation between the measurement precision and disturbance. But you need to carefully define what it means by the measurement noise or uncertainty and the disturbance, and thereby introduce new inequality. And the lower bound would always be related to the anti-commutation. So this means that if the two observable commute, in principle, they can be simultaneously measured and arbitrarily precise. Okay, so that's the sort of interpretation and understanding of Heisenberg's uncertainty principle. I'm going to give a derivation of this. For example, we consider two operator, they are Hermitian. So when we say observable, we implicitly assume that these are Hermitian operator, meaning that A dagger equal to A and B dagger equal to B. this is important in the application because the uncertainty, let me just stress, this is important. So uncertainty relation does not hold if A and B are not Hermitian. So for example, you may say, okay, an A dagger, if you remember, these are boson operator. Their commutator gives rise to identity, and then you would conclude measuring delta A and delta A dagger is greater than 1/2. This is not correct. Okay. Okay. In our derivation, yes. You have question? Can you say louder?
Do you mean they do not hold if they're not Hermitian?
Yeah, you cannot derive such relation.
Yeah, you
but you could introduce some Hermitian. Then there will be a correct. You could derive a new set of observable, right? As long as you make them Hermitian. I'm saying that if you cannot naively apply this formula to any operator, A and B have to be Hermitian. Okay.
Yeah, it's just on the note you wrote they are Hermitian, which should probably be they are not.
So when we say observable,
He means there's a typo in your note. A and B are not Hermitian. The red pen.
Or am I?
Are not. Yeah. Okay. Thanks. Yeah, it's probably saying is faster than writing. So yeah. Okay, but we can see that from the derivation. So we can write A times B in terms of the anti-commutator and commutator. Well, this is just a simple identity, right? And I write these as A anti-commutator B and then A commutate with B, right? So why do I want to write this? Because if I write that, because this is symmetric, and individually they are Hermitians. When you take dagger, this is the same as this Hermitian conjugation. This is the same as that, because when you take the dagger, Hermitian conjugation, you flip this, and this is the same as AB because they are Hermitian and symmetric. Okay. So therefore, the first part is real, while the second part is pure imaginary, because AB dagger has a minus sign. Okay. So therefore, you can write this expectation value. As you can see, product of Hermitian operator need not necessarily be Hermitian. So its expectation value is in general a complex number. So you can write the real part and imaginary part. Okay. And let me erase this. So if you take the absolute value square, so then you are writing these square and adding these square, it is x squared plus y squared, right? And which is the total absolute value square. And the right hand side using Schwarz inequality, you can upper bound by this expression. Okay, essentially this is A dot B. The inner product square is less than individual product of individual norm square. Okay. Yeah. So as I said, the Hermitian operator property is used in deducing that this part is real and that part is imaginary. Okay. So basically here, if I retain just one part of it, then this would hold. Right? This would still hold. This inequality upper bounded by this will still hold. Okay. Yeah, this is just dropping the real part, you get this inequality. Okay, and it's almost the uncertainty relation, except that I need to subtract the average part. So simply I replace the observable A by A minus a constant, B, replace B by B minus, this should be B. So let me correct that. Yeah, so simply replace the operator by itself subtracted by the average. So this inequality would hold, and the commutation would preserve. So A minus expectation value, B minus its expectation value. The commutator of that is still A, B, because the constant always commute. Okay. Yeah, therefore I get this. And by definition, my right-hand side are the delta A square, and this is delta B square. So I just swap the left to the right and flip the inequality. Okay, so that's the derivation of the uncertainty principle. Okay, so this is what I mentioned earlier. That's what we derive. Okay. Okay, and one of the consequences, the uncertainty relation between momentum and position. Okay, any question on this? Okay, this inequality is probably one of the most important in quantum mechanics. It's probably one of the first few equation that you learn about quantum physics. Okay, any question on the derivation? Okay, this is not how Heisenberg derived. This is a more modern way of deriving the uncertainty principle. Okay, we can look at one consequence. So let's take these position and momentum uncertainty, right? So we're going to see when the time evolves, the idea of wave packet would expand. So as I already indicated here, suppose I have a wave packet and I let the system evolve, and I expect that this would expand. So the reason is using this uncertainty, so I can roughly define the uncertainty in the velocity. So that will be the uncertainty in the momentum divided by the mass. And using this uncertainty relation, I replace delta P by h bar over 2 divided by delta x, and I get this. And suppose initially this is the uncertainty in position. After time t, I expect that because of these uncertainty in the position in the velocity, it adds more to that uncertainty. So that's just velocity times time. This is basically delta V times t. Okay. So that gives rise to such a spread in the uncertainty. So then we can ask when is this minimized? Okay, so if we minimize this expression with respect to the delta t, and we find that this essentially what you get is the two would roughly be equal. So, yeah, I mean you can really just take the derivative with respect to delta x and try to find the extremal value, but roughly this term increase with delta x, this term decrease. So somehow when the extremal value occur when these two balance. So when they balance, this means that this holds, and that means the minimum would be just the square root of h bar t over 2n, right? This part is the square of delta x. So if we minimize this expression with respect to delta x, we find the so-called standard quantum limit. The SQL, standard quantum limit, is the h bar delta t over 2n over the delta x that we found here. And that's this expression. Okay. So this means that if I have a wave packet that has such uncertainty in position, then it will not expand too much, and the optimal time we measure is it's the with respect to the delta x, it's optimized at this value. Yeah, and that's this as a function of time. So this is the minimal wave packet you can have. Okay. So you can also extend the uncertainty to the other pairs of observable, such as the phase and number. It turns out that their commutator satisfy this relation. So the commutator of the two equals I, and therefore you see that the delta phi is greater than 1 over 2 times delta n, meaning that if you want to measure a phase, its uncertainty is lower bounded by this expression. So, and this roughly 2 delta t is roughly also lower bounded by 1 over the total number of photon, total number of particles. In the case of photon, this would be the photon number. Okay. So it seems that there is a limit that in the uncertainty that we cannot beat. This is usually called the Heisenberg limit. Okay. So Heisenberg limit is about measuring a phase. There's a limit, and the standard quantum limit is about measuring the position. Okay. So that's the consequence of using the uncertainty principle. Okay. Yeah, so there is a very nice paper by these authors some time ago. They raised the questions and they provide some resolutions. So for example, you know the uncertainty always there, so how do you deal with that? So they propose, for example, you can monitor one out of a set of incompatible observable. You don't want to observe two incompatible ones. Of course, this is just to evade the problem in some sense, avoid the problem. Another suggestion is to employ a quantum state in which the uncertainty in the observable you want to monitor is small. So this is at the cost of uncertainty in the complementary observable. For example, delta x and delta p has this. And in terms of the so-called coherent state, we learned that in this XMP, the coherent state is some kind of blob in the sort of Wigner representation. Remember we showed this when we talk about the cat state using coherent state. And you could squeeze one directions. For example, you could squeeze. So to have the delta x to be small, but the delta p would be bigger. This is called squeeze state. So in some sense, this suggests that you might want to use squeeze state. For example, if you want to measure, for example, some oscillations, and you may want to prepare a squeeze state. So this could be in the application of the so-called LIGO that is used to measure the gravitational wave. Okay, they also discuss source of error. For example, environment-induced noise from fluctuations such as vacuum. This is the so-called shock noise. And also some noise induced, for example, in the position measurement of a particle. And we already mentioned this is a standard quantum limit. But these are not fundamental limit, not necessarily fundamental limit. As we said earlier, the delta A and delta P, in the way we derive, these are not necessarily the measurement error and the disturbance. So it's possible to minimize the disturbance further. Okay, so maybe let me give an example. We've seen this Mach-Zehnder interferometer before. So the setup we have is as follows. This, you have some light, and it goes through some beam splitter here and split into two. In one of the arm, you put a sample, which induce some phase shift phi. And at the end, here they combine, and there are two ports. You put a detector behind each port, and you measure the intensity. Okay, so when I introduced Mach-Zehnder interferometer earlier, I was discussing in the context of a single photon or a quantum particle. But this interferometer can be used also in the classical setting. So when you observe this, as you vary the phase, if you could, you will observe the intensity from one of the detector to be oscillating as a function of the phase. Okay, so let me just not going into too much detail of the classical understanding, is really just using interference. Okay. Yeah, so it seems we more concerned with quantum mechanics, so I'm not going to read through the detail, but you could read that. Instead, I'm just going to refresh you the homework problem 1. So I hope you still remember this homework problem. Okay, so remember we have a special rule. If a quantum pinball, it could be a photon, electron, goes through a beam splitter, we get a amplitude 1 over square root 2, and if it's reflected, we have I over square root 2. So the problem there asks you that if we have a phase shifter theta here, assume that this add additional phase, and I ask you to calculate the intensity. So that's exactly the quantum case for this one. And this is expressed in terms of probability of a particle going to here. right? So you still remember how we solved this problem, right? So essentially we are using interference. So for example, the probability going to A comes from two paths, right here, right? And another one is transmit first and then reflect, right? So, and we have to add the amplitude of these and then square that. So let me just write PA theta is that. So how do I do this calculation? At here, it's a reflection. So I put I over square root 2. Here I have theta. I put e to the I theta. Here I have 1 over square root because it's a transmitting. And this one here is the reverse. You first transmit. The lower arm does not incur any additional phase. So just put 1. And here it reflects. So I have a square root I over square root 2. Okay, and I square that. And these are 1/2 and 1 plus e to the I theta square. Okay. So basically this is 1 plus cosine theta over 2. Yeah. The other port, the probability will be this. Okay. So in terms of intensity, the intensity at I would be just intensity times the probability. So this should apply to the classical as well. Okay, so this is the homework 1 problem, and you have all solved this. Okay, I think that this part is cosine square theta over 2. This part is sine theta square over 2. Okay. Okay, and yeah, okay. I was using theta here, but I use phi in this picture. So that's the intensity coming out at detector 1, intensity coming at detector 2. Okay, so we can talk about the uncertainty in measuring the phase. Okay, so suppose we are detecting photon and we just measure the clicks of the detector, and we assume that the photons are independent. Then we can first look at the uncertainty in the difference of the intensity. So let's say I1 minus I2 and the overall intensity divided overall intensity I0. This is sine theta, right? This expression is basically cosine theta over 2 minus sine phi over 2, which is cosine 2 angle of the argument, so it's cosine phi. So if you look at the variation of that, would be just sine theta. There's a minus sign, but when we talk about, we only care about the amplitude, magnitude. So this, as you can see, it should, because the photon number comes, the photon comes independently. So we know that such uncertainty would be just like the random box will have a 1 over square root n. So we see that delta phi is proportional to 1 over square root n. Okay. So this is the sharp noise limit. Yeah, so this, the uncertainty interface in measuring this phi from the sample is limited by the number of photons. Okay, so that's this sharp noise. This is called sharp noise limit. Then you, of course, you can ask, can this be overcome? Of course, the answer is yes. as I mentioned, that you could use a squeeze state. This was proposed first by Carl Cave in 1981, and later there are also other references on that. If you use a squeeze vacuum instead of the original here, this is vacuum, right? Here there's no input, or meaning that this is vacuum. But if you can input some other state from here, you can show that the uncertainty in the phase can perform better than 1/√2, meaning that this is smaller than this. In this particular example that they show is this scale as 1/n raised to 3/4 power. Okay. And indeed that this can actually be further improved, for example, using some kind of entangled state. Entangled in the sense that this mole and that mole are entangled. So as I'm going to illustrate next. Okay. Yeah. So this is something called Nunn state. So here we are not thinking of, we're thinking of you could input a state that goes to two arms like that in a so-called Nunn state, meaning that in the A you have n number of photons, and in B there's no photon, and that's superposed with in the A mode there's 0 photon, in B mode is n photon. So this is called n 0 0 n state. So that looks like a Nunn. And if you have phase shift in one of the arms, let's say the A arm, because each photon contributes to e to the I phi, and you have n photon, the phase accumulate to e to the I n phi, right? And the second part has no photon in A, so you get this. So if you were able to mix the result like this, if you were able to mix and then perform the detection, if you could detect n photons in the output, if you can count the number of photons, you will see that this oscillation will be anti-faster than if you have only single photon or uncorrelated photon. So this is similar to what I have before here, except that the phase is n times as large. Okay. So this means that the uncertainty would drop by a factor of n. So it would have a factor 1/n here. So this can reach the Heisenberg limit. Okay. Yeah, such Nunn state has been created before. This is shown here by this paper. This is a so-called Mach-Zehnder interferometer, and this is how they create. So if you're interested, you can refer to this paper by how they create this in detail and how they detect as well. But I want to show you the oscillation, if they could change the phase and observe the interference. So if you have two photons and the horizontal axis is the phase, we call it Mach-Zehnder phase. This is phi. If they can change the phase and they look at the detection, so in the case of two photons, this oscillate like that. Okay. And in the case of three photons, it oscillates faster as a function of the phase. In the case of 4 photons, it oscillates even faster. The 5 photons perhaps is not well, the fidelity with the ideal Nunn state is not so good, so this oscillation it's not so regular, but you see that it oscillates faster than the other cases. Okay. Yeah. Any questions? Okay. If there's no question, I'm going to introduce a more mathematical formalism. So far, we have been rather hand waving using uncertainty relation, right? And we try to argue a few different cases. So there is a mathematical formula which is more rigorous. It's based on the so-called Fisher information and Cramer-Rao bound. So let me introduce the setting. So as before, the goal is to estimate an unknown parameter theta. It could be a multiple parameter. Let's just use the simple setting. Then we only want to know this parameter theta, and what we want to know its uncertainty when we estimate that. Okay. So that assume there is a measurement. In this case, could be classical. Let's just assume we're talking about classical measurement. And we measure some x. Okay, we measure x. Okay, we measure this. And the measurement give some value x. And that assume it has some distribution. Okay. So if the parameter is theta, there's some distribution f. And suppose we read and the meter that detect maybe a particle or the number, and we get a value x1. Then we want to estimate the value theta. Okay, assume that the estimate is given by some function t. We just say if it's t1, there's some rule that's described by this function t, and it gives us an estimate. Okay. Okay, so then we want to estimate the value theta. So the setting is that if this measurement is precise and then you repeat many times, in the limit of you perform many measurement, you average over your estimate and the distribution, we will get precise, accurate, exact value of theta, assuming this is the ideal case. So basically, t is just a way allow us to estimate theta. Okay. Okay, so that's the setting. So this is basically the setting. So you assume that we have a way to estimate by reading some meters that we know how to estimate the angle theta. Okay. And I assume that with sufficient statistic, we can get the exact value. Okay, it's like shooting a target, assuming you do many and you're aiming that very well, but there could be some fluctuation. But if you do it many times, you would have a peak at the center. Okay. Okay. So next, I'm going to define Fisher information. This in terms of the interpretation, this is the so-called related to the so-called log likelihood function. So basically, that's this log likelihood. Likelihood basically is the distribution, right? So it really is asking how this log likelihood function varies with the unknown parameter theta. So how it varies, we just take the derivative, right? So and then take the square, average over the distribution. This is defined as the Fisher information. So that's the definition. So it's conveniently right as a bracket. This is the thing that you want to average, and you are averaging with respect to this measure. So sometimes we put theta just to indicate it that this function f of x slash theta is the measure used to evaluate the expectation. Okay, so this is so far this definition, but we're going to see that this Fisher information is really useful in estimating the lower bound on the uncertainty of our estimation. And this is the so-called Cramer-Rao bound. Suppose that I perform this n-independent sample or experiment according to the so-called Cramer-Rao bound. The uncertainty in estimating the theta, let's label it delta t, is lower bounded by the square root of number of repetition and square root of the Fisher information. Okay, it's hard for me to write the I because I think the PowerPoint function down there. So let me just erase this and write. Okay. Delta t greater than, this is number of repetition. And this is given from the Fisher information. Okay. So I want to mention that this was taught in applied math by 71. If you're in applied math, you might have already have heard of this. So who have, maybe let me just pause and see who have heard of either Fisher information or Cramer-Rao bound. I know there are a few applied math students. Okay, at least one of you heard. Yeah. And this is the standard tool in mathematical statistics. Okay. So I'm giving you the result of that, but I'm going to give sketch the proof. So let's just consider there's only one sample, okay, and we want to derive this. And how we derive this is convenient to introduce the so-called covariance between two functions, g and h. So we define in almost like a standard deviation, except that you have one function on one side is g, the other is h, and this is defined as the covariance. The angular bracket is the average, okay? So when we specialize this to t, t is our estimate of the angle and whose average is theta, right? So if this is t, then this will be theta. And we want to choose the h function to be this, the derivative with respect to the log of the distribution, okay? And what is the average of this? So the average of that turns out to be 0. As you can see from this expression here, this is the definition. And you take the derivative with respect to that. That's f the derivative of x with respect to theta divided by f, because this is a log. Okay, and that f cancel this f. So you're left with this, and you pull the theta outside. And since this is a distribution, it integrated 1, therefore it's 0. Okay, so when we specialize to these two functions, t and capital L, we would have the covariance defined as this. If this is theta is the expectation of t, and this expectation value is 0, so I just drop that. Okay, and you could use this again. This theta is a constant. The expectation, if you expand this, this is t times this derivative of L, theta times that, and because this expectation value is 0, so you're left with this expression. Okay, you just plug in the definition as I did here. That give rise to canceling these f, and you are left with a derivative with respect to theta, and then with respect to t, and this is 1. Okay, because this, let me just go do one more step. This is that, and in our assumption, this is theta, and that's 1. Okay, so we have derived that the covariance of these two functions is 1. And then next we're going to use similar to what we derive in Heisenberg uncertainty, we're going to use the Cauchy-Schwarz inequality, namely that the variance of G and F, product of variance of G and product and variance of H, by definitions, this will be greater than the covariance square. Okay, so that means we can write delta t square. Okay, so delta t squared, I think this is just a shorthand notation of that. Delta t squared times delta this is greater than the covariance square, right? So that's I squared. Sorry, that's 1. Because we derive the lower bound is 1. But I want to know that this is the visual information as defined here. So because delta L theta L, this is defined as square, because its expectation value is 0, and that's just by definition, that's this. So one side of the variance give me visual information, so that give me delta t squared times visual information is greater than 1. So therefore I get delta t squared is greater than 1 over the visual information. And n sample, I just put it back because if you consider doing this n time, you have a factor of n here. Okay. Okay, so if you haven't seen this proof before, you might want to go back and rederive it yourself. Okay. Okay. So of course, the next natural thing to do is to extend it to quantum case. So in our quantum case, I'm not going to do a full derivation. That's just to sort of give intuition to expect what we should have in the quantum case. And we also, assuming we're only evaluating one parameter, and we have some quantum state that goes through some quantum channel or quantum operation. We just denote rho theta is the action of phi theta on rho. Okay, so that's this rho theta. And we want to, from the output of this state, we can perform measurement, and we want to know when we estimate the theta, what is the variance? Okay, and first we have to ask, because there is this L log likelihood function, how do we generate this? Right, so remember the L is log of the distribution. So how do we generate that? So more precisely, it comes from some measurement. So I would have to define a measurement operator, and then f of x slash theta would define as rho theta. And when you perform the measurement, obtain the outcome x. Okay, but if I ignore this precise definition, I would roughly say that my distribution is described by this density matrix. Okay, and then log of this is like the derivative of the log is like derivative of rho divided by rho. Okay, and suppose that this derivative give rise to d times rho, then I write this as theta. So this log f derivative with respect to that give me theta, d theta. Okay. Therefore, the Fisher information, which was defined as the expectation value of this quantity, we can generalize to, because expectation would be respect to the density matrix. This is roughly our d theta. Okay, so we would expect our Fisher information to be of this form. Okay. Of course, yeah, if you want to make it more precise, you have to use this, but let's not do that at this point. So I argue that sort of the derivative of theta rho with respect to theta is proportional to d times rho. It turns out that because this operator you should define more carefully, it's actually more precisely defined as the anti-commutator. So anti-commutator, this expression is defined this way. Okay, instead of d times rho theta, as I sort of naively expect here, I should replace that by the anti-commutator divided by 2. Okay. So then we expect the quantum Fisher information is this, and then therefore the quantum version of Cramer-Rao bound, which is nothing but just saying the uncertainty in estimating the angle or the variance is lower bounding by this quantity, by the Fisher information and this number of sampling. Okay, so that's the expectation, what we expect. Okay, so we're going to just look at these expressions and derive what D should be. Okay, so that's what I'm going to do next page. Okay, so any question on this? So this part is hand waving, because I want to really compare with the previous classical case. This part is more rigorous. Okay, but I want to give a derivation of what I should get and to infer what D should be if I use such a definition. Okay, any question on this point? Yeah, this part is slightly more abstract than what we began with, but this is the important mathematical foundation. Okay, so this is my definition. In some sense, you can regard this as the definition of d theta. Okay. From this, we're going to derive. Okay, so I already wrote this in advance. So if I expand this expression in terms of a complete basis, so basically I just insert an identity on left and right, right? And I define this as the Aij. Okay, if I keep writing, and then use the property or the definition that I define that this J is in the basis of eigenstates of rho. So I can expand in that complete basis. Okay. So rho acting on this part, give me a lambda J. Rho acting on the left, give me a lambda I. Okay, so I have this expression. Okay. Yeah, and Aij is nothing but the expectation value on this. Okay. Okay. From here, I can infer my d theta because I can also expand the d theta in the same basis. Right? Basically, if I find this, as I want to find this. By comparing to the left and right hand side, I should identify this part times 1/2 being the same as Aij. Right? Therefore, d theta is twice, so moving this 1/2 to the other side, A over lambda I plus lambda J. But here I should make a constraint. If this summation is 0, then the inversion of that has no meaning. So I should just leave this out. Okay, so that's the constraint. So yeah, in the following, I will probably now write this. Okay, so this gives us a definition of the d theta. Okay, d theta is roughly the coefficient in front of rho prime, where prime is the derivative respect to theta. Okay. Yeah. Yeah, and that's and then we could apply the Cramer-Rao bound. Okay, so once we have the expression d theta, right, so we can evaluate I theta, which is trace rho theta d theta square. Okay. Yeah, so I did not provide the proof because this proof require you to really go through the rigorous of defining this distribution function and going through some inequality, but I will not go through the proof in detail here. Okay. I think I might have cited the paper that you could go just check out the proof. If I see the reference, I'll point it out. Okay. Any questions so far? I mean, this is sort of more abstract derivation or formal derivation on this d theta. Okay. It's as if we were deriving what this should be. Okay. Okay, so yeah, so if we consider a special case where the action of the channel is really just unitary, so suppose this is some unitary, it could be an evolution or could be some phase shifter. Suppose the state evolve like this. So if it's a pure state, . you would evolve from psi, acting on this unitary. Let me define as this as phi theta, psi theta. Okay. And this is our official information. This is what we already derived. And it turns out that in this case, G here is the generator of this unitary gate or unitary matrix. You can actually derive what the feature information is in terms of these eigenvalues of rho and eigenstate of rho. Okay, so I will not go into the detail of this. It's actually in the next page. And this is generally for general mixed states, but for pure states, so I will pose as an exercise that the expression looks much simpler. It's actually the generator, which is emission here. It's actually the variance of the generator, okay, defined this way, okay? And from there, then we can immediately use the bound to estimate the uncertainty when we as measuring the angle, okay? There's some derivation. I'm not going to the detail, just to let you know that I derive that expression here. Okay, you can check out later yourself, but I'll skip the derivation. Any questions? So maybe it will be clear if I illustrate with examples. Okay, so suppose I consider a coherent state. Coherent state is a typo. So I hope you still remember coherent state. So these are states that behave really like a classical oscillator. So if you take the annihilation operator acting on the coherent state, it will just return this coefficient alpha. Okay, and you can evaluate this efficient information because that's really just the variance of that. So let me just write the variance is really just a dagger A square. Okay, there's a factor of 2 minus alpha A dagger A over 2 square. Okay, so there's overall 1 over 4, and this part is easy because A acting on alpha pull down an alpha, and this act to the left pull down its expectation complex conjugation. So therefore this is the square, and this part A dagger A square is this, and you want to evaluate that. So what you will do is use the A times A dagger is A dagger A minus 1. Okay, and that if you expand, it's A dagger A minus A dagger A. So expectation value with respect to that, we already calculate it's alpha square. To that, you act twice of A on the alpha, so you bring down alpha square, and to the left, you bring alpha star square. So it's alpha square, so alpha absolute value to the 4th. I think this is plus, okay? Plus alpha square. Okay, so we get alpha absolute value to the 4th power plus to the 2nd power. So we're left with 1 over 4 alpha square. Okay, and the factor of 4 is here, cancel that. So we get IQ, the Fisher information, the quantum Fisher information is alpha absolute value square, which is the average number of photons. So if we use delta T the uncertainty in the estimation would scale as 1 over square root of average number. Okay, so that's the shot noise limit. So it asks, so the coherence state asks us if it's like a Poissonian distribution. So there's a random photon number just appearing at the detector. You could also look at the so-called Fock state. It's a definite number state. Definite number state has no fluctuation in the number. So the Fisher information is 0. So that means it's probably not useful to use in estimating and in estimating data. Okay. But it's useful if you look at the superposition. Suppose I take 0, it's a vacuum, and superpose with n, and I would assign this as an exercise. You can show that this Fisher summation is actually n squared. So this gives rise to a Heisenberg limit. Number of samples and 1 over n. Okay. Okay. Yeah, so I want to just mention when the input is pure, then the expression simplify a little bit with respect to the derivative of the state, the pure state with respect to the angle. Okay. You could also generalize to multiple parameter if you have and a few parameter theta to estimate. Then this will be a matrix. For those that are familiar with Berry phase, it looks like it might be related to Berry curvature, but I'll leave this subject out. Okay, so probably this will be the last example. So if we have been considering the so-called single mode because there's just one mode. If we consider multiple mode, for example, 2 mode, meaning that there are 2 different paths in this particular example here. And we're going to consider G to be the difference of the 2 number. So dagger A is, for example, A will be in this direction, and B is in this mode. So that generator will generate a phase difference between the 2 paths, right? So if you have a photon going to this direction, it would give rise to e to the I minus theta over 2. If it goes to that, it would give rise to e to the I theta over 2. So it's more a symmetric version of the Mach-Zehnder interferometer. Okay, but the relative phase is e to the I, e to the minus I theta. Okay, so you can estimate the variance if you use a coherent state. Let's say use the coherent state. So that goes to here as alpha, that goes there as beta. So here I don't care about these spin splitter here. Assuming I can input a state in both arms in this form, alpha tensor product beta, and you can evaluate the Fisher formation using the formula given here. And it's simple evaluation, just like what we did for the coherent state in single mode. You see that the Fisher formation is really the total number of photons. So this is shot noise limit. Okay, so depending on the source that you send in to probe the phase, in this coherent state case, is a shot noise limit. If you use the Nun state, meaning that there are n photon in port A, 0 photon in port B, superpose with 0 photon in port A and n photon in port B. This is called Nernst states. You can evaluate this Fisher information, and you can convince yourself this Fisher information is n squared. And this reach the so-called Heisenberg limit. Okay. Any questions? Yeah, I know. Yeah, this part is slightly more mathematical, but this is. I hope these examples illustrate the use of quantum Fisher information. Okay. So I think that's the end. So I want to congratulate you on completing 13 weeks of 25 lectures in this QIS course. I think this translates into, I think, 2,000 minutes. Okay, so I think that's an achievement. You should give yourselves applause. What's next? In spring, there is a course on quantum computing offered by Professor Korapin. It will contain more advanced topics. I encourage you to check out his course. And in the remaining 3 classes, it's not me doing the solo lecture. It's going to be your show. So you're going to present. There are 7 groups. Yeah, so these are the schedule. So the first day after the break, group 1, 2, and 7 will present. The second day on Wednesday of that week, group 4, 5, 6, and the last day will be group 3. Okay, and these are the topics that you guys have gone through. A lot of content, a lot of material. We have gone from 0 to a lot of information. So I hope that this give you a good overview of quantum information science. And I believe that by now you'll be able to understand a lot of development, current development, or if you find interesting in any specific topic, you have enough background knowledge to dig into more detail. Any questions?
Professor, I have a question.
Yes.
You know if the lectures will be available online even after the semester is over?
I think it should be available through Blackboard.
Okay.
But I've been uploading this to YouTube, so it would be there forever.
Oh, I didn't know that.
So if you go to my course website, yeah, if you go to, can you see, or maybe I should switch the sharing. Yeah, so I put a lot of references on the course websites. I keep adding that. It's not convenient to do this in the Blackboard because there will be like a separate post. But in the Blackboard, I do upload the slides and there are links to the recording, as you can see. But in this course website, it's more convenient for me to put all the information, like suggested reading and more references. You could click and you could go to the references. And I started migrating these recording to YouTube, so you could click the link and it will be there. So if you know other people interested in knowing more about quantum information, you can maybe just suggest them to go to the lectures.
Thank you.
Okay. Let me switch back to the slides. Okay, any more questions? I think you should give yourself a round of applause, which I will do now.
Same for you. Thank you for a semester of amazing topics.
Thanks for all of you who stick around until the last lecture. So,
you.
but I look forward to your presentation after the break. Okay, thanks. That's
Okay, thank you.
Thank you.
Bye, everyone.